Okay, so we're going to look at something called an algae tile, and we're going to use those to investigate collecting like terms with algebraic expressions. So by the end of today, I should be able to recognize like and unlike terms, and I should be able to collect those using the operations of adding and subtracting. Okay, so algebra tiles can be used in a bunch of different ways. We kind of used the idea when we had our zero principle and our integer discussion. Right now we're going to be using it here in terms of like and unlike terms. And you can see that there's some value in learning about them because in part 3 we can get into a whole bunch of more challenging concepts. So let's just go through how we come up with some of these algebra tiles. So if I have a area or a square that's 5 by 5 and I have the area of a square that's 7 by 7, if I look at those shapes, okay, so you can see the sides are 5 by 5 in the first one, I get an area of 25, and I would call this, you could write that as 5 squared inside. The next square is 7 by 7, it would have an area of 49, or we could say that's 7 squared is the area inside that blue box. Okay, if I ask for the area of a 1 by 1, you can see here, so this would be 1 squared inside, and it would have an area of 1. And that leads us to the piece we're really looking for, and that's what is the area of a square that has a length x by x, where x is some unknown amount we don't know. Okay, well that area inside there would be x squared. Okay, and the key piece to recognize here is that there are limitations with how we can draw these shapes. This x squared here, just because it is the same size as the 5 squared up here, does not mean that x is 5. They're just some of the limitations of how we can represent or model mathematics. There are some restrictions on how big we're going to draw something on a piece of paper. So when we look at this term right here, what this means is we have two unknown values that are the same value. We just don't know what they are. And when we multiply them together to get the area is x squared. Okay, so that's a bit of an abstract concept. We can continue that same discussion. What if we have a rectangle that's 5 by 1? Okay, well the area of that rectangle would be 5, whatever unit squared. If I have a rectangle that's 7 by 1, the area of that rectangle would be 7. Now if I extend that concept to what is the area of a rectangle that has one unknown side and a width of 1? Well, that would be x times 1, so the area of this shape would be just an x. Okay, so the x represents the area of that narrow rectangle. Okay, so that brings us to our algebra tiles. So we will have both positive and negative. I tend to show positive as blue sometimes. It doesn't really matter. As long as you're consistent within the problem, the color's not really a big deal. So if you're looking at this first term here, this is our x squared term, our x, and our 1. And then I use red, or the textbook sometimes uses red to represent negative. So this would be negative x squared, negative x, and negative 1. And all of these pieces inside just represent area. Okay, so we'll be able to take advantage of the zero principle. So a positive x squared and a negative x squared will cancel each other out. A positive x and a negative x will cancel each other out, and so on and so forth. Please note different textbooks will use different colors. It doesn't matter as long as you're consistent throughout the problem. Okay, and then this one here, I know our textbook uses this for sure. You can have other terms represented. So if you have a term x, y, that might just mean you have a rectangle with an unknown x on one side and a different value, unknown y, on the bottom. And again, the actual size of these shapes isn't that important. They're just representations of areas we don't know. So don't get too tied up in trying to think about how big they are. The only rule we're going to find for algebra tiles is that like sides have to touch. Okay, so these both have x's as that dimension, so these two sides could actually touch. You can't put the other ones in other locations, but we'll get to that in a future lesson. Okay, so when we talk about something called a monomial, mono, singular, being the key prefix there, we're talking about one term. And I like to use the algebra tiles because it really helps to see. Here's what 5 looks like when you use algebra tiles. And immediately you can see, hey, they're all the same shape, they're all the same color. Cool. Here's what 4x looks like. And again, they're all the same shape, they're all the same color. Negative 2x squared. Same shape, same color. Now what you can see very quickly with this picture is that there are 3 different shapes, 3 different colors, and we would call those unlike terms. Okay, so an x and an x squared, they're not the same, so we can't count them or combine them together at this point in time. Okay, so those are monomials. A binomial is 2 terms, so consisting of a constant and an unknown, 2 unknowns, whatever it might be. So this first one here might be x plus 5. And you can see pretty quickly there are 2 different shapes, 2 different colors. So that's why this is a binomial. 2x minus 6 would look something like that. And I'm going to drag a bunch of negative 1s over. I'll cheat and do a clone. There we are. So there's 2x minus 6. And again, you can see 2 separate colors, 2 separate shapes. And then lastly, negative 3x squared and plus 4x. 2 separate shapes, 2 separate colors. I might have just put those off my screen here. There they are. Okay, so that's a binomial. And then lastly, a trinomial is 3 terms. So you can see there's an x squared. There's the negative 2x, different shape, different color. And there's my 1s. Should probably use a number smaller than 5 to make this dragging a little faster. 3 different shapes, 3 different colors. Okay, now if we look at negative 2x squared plus 3x minus 1, the next question, again, there's your x squareds, there's your x's, and there's your negative 1. Okay, so those are trinomials. You can see there are 3 separate, distinct shapes. Okay, so collecting like terms, you can only collect terms that are the same shape. So in this case, I have 3x plus 4x. Now we can see these are all the same shape. They're all x's. Okay, so if I counted those up, I would see I have 7 of those shapes. So we would say this is 7 x's. Okay, and the one thing I really want to point out is notice the exponent did not change. We just counted the number of these tiles that we had. Okay, so try not to confuse that with our exponent rules we learned the other day. All right, so let's try another one. If you want to pause it and take your best guess, we can do that. Okay, so 2x plus 3x. I'm going to go 2x here, plus 3 more x's, and negative 4 1s. Okay, and I should be able to see very quickly I have a total of 5 x's. And because the negative 1s are a different size, different color, then I can't combine them with the green x's, so I have 5x minus 4 is my simplified term. So just these guys have combined. Okay, again, if you want to pause it and try it first, you're welcome to. You're probably starting to see a shortcut brewing here on how we can get to these answers without the tiles. But pause it and give it a whirl. I'll start laying it out here. So we have 3x squareds. We have 5x's. And we have 2 negative 1s. There's the first 3 terms. To that I have to subtract 2x squareds. I have to subtract or use 3 negatives for the x's, and I have 5 positive 1s. Gotta stop using 5 here. Okay, now what we can see very quickly, I hope, is we have some 0 pairs. Okay, so if I have these 3 x's down here, these negative x's, if I pair them up with 3 green x's, all of these guys right here 0 out and cancel. If I take these 1s they zero out and cancel. If I take these x squared terms, they will zero out and cancel as well. And my final answer is whatever's left over. So I have 1x squared, 2 positive x's, 3 positive 1's. Okay, so as you start to do more of this, you'll start to notice these two here, including the sign out front, these two here play together. These two here play together. And then these two here play together. That's where we start to get into some algebraic shortcuts. There are some things to worry about. The sign in front of the term has to stay with that term. So this is a negative 3x, no matter where you rewrite it. Okay, so you have to be able to keep track of that. Okay, so pause this one. Try it either with the algebraic shortcut, or if you want to draw tiles, you're welcome to. Okay, I'm just going to start setting it up so we can see it. There's the 2x squared. There's the 3x's. Oh my goodness, minus 7. 2, 3, 4, 5, 6. Oof, 7. Oops, come on, all of you. Okay, now I have negative 4x squared. Oh boy, you can see how the tiles, if we had large numbers of these, would start to be difficult to work with. 1 negative x and 3 positive 1's. Okay, so again, this term, which is just whole units, and this term are going to play together. So negative 7 plus 3. If we bring those 1's down, those cancel, and we are left with negative 4. Okay, so there's part of our question. These guys here, the negative 1x and the 3x will play together. They will zero out, and I'm left with just 2x. And then lastly, I need to bring 2x squareds up here. Two negative x squareds up here. They will cancel the positive 2x squareds, and they're gone. And this is what I'm left with. So this would be negative 2x squared plus 2x minus 4. Cool? So the key thing to remember with like terms is everything after the coefficient. The number is the coefficient. That's how many there is of something. Everything afterwards has to be the same. So an x squared term can only play with another x squared term. An x term can only play with an x term. Okay, so like terms must have the exact same variable after the coefficient, same shape in your algebra tiles, although the order does not matter. Notice when adding or subtracting the exponents, do not change. Okay, this is a big idea right here. So in no time in any of those previous questions did the exponents on those terms ever change. Okay, so here's some examples of like terms. So these are like. So 4a and 5a, you can see everything after the coefficient, everything after the number is the same. Down here, 6ab, 7ab, negative 9ba. Is that a like term? Well, it is, because we've talked about the order of multiplication doesn't matter. So you could rearrange that and write it as negative 9ab, and then it fits with the other three. Okay, the last one, everything after the 8 and after the 2 has to be the same. So we have an x squared y, an x squared y. Those are like terms. Unlike terms. This one's pretty easy to see. We have two different letters. Okay, the second line, this is an a squared b, an ab squared, and an a cubed b. Those are not the same. Okay, even though they have a's and b's, the exponents make them different. Okay, and lastly, x squared y squared and x squared y are not the same. If you want to know what that looks like, if we were to expand it, it would look something like this. And you could see very clearly that this one here and this one here are not the same. Okay, so we also sometimes have brackets that are introduced. So we have to look at this as collections of groups. So 3x plus 1 is one group, and to that we're going to add 2x minus 5. Okay, and the nice thing about the adding operation is it's pretty logical. It's the subtracting one that normally gives us issues. So if we're just combining these, we have 5x's, We only have one zero pair that cancels off. So my final answer here would be 5x minus 4. Okay, so again, we have two groups being added together, an x squared plus 3x plus 1. That's one group. And to that, we're going to add a second group of 2x squared minus 4x minus 3. And again, there's nothing that's going to zero off on the x squareds. There's 3 x's and negative x's that will cancel each other out. And there is one whole unit of 1 there that can cancel, so those all go away. And this is what we're left with. So the answer here, better give myself some room, is 3x squared minus x minus 2. Okay, and again, if you can see this without the tiles, that's awesome. I just want to make sure we have an understanding. Now, subtraction we got to be careful of. Subtractions can be nasty. Okay, so let's just go back to a real basic. Here's 3 ones. This says take away 5 positives. Well, we don't have 5 positives. So we may have to introduce some 0 pairs, just like we did with the integer chips. So now when I take away my 5 positives, I actually have something left over. So this is negative 2. Okay, so now we're going to really be careful with subtraction. So we have, 2x plus 5. Okay, there's my 5. And now from that, we want to subtract x plus 3. Well, I have an x I can subtract, and I have 3 I can subtract. So if I take those away from that pile, this is what I have left. So this would be 1x plus 2. So what we need to be careful of algebraically is there's nothing around this first bracket, so I don't need to keep writing it. But this subtraction right here goes to both terms. So you are subtracting an x and subtracting a 3. That's the really important piece from an algebra standpoint. And then if you look here, 2x minus 1x is 1x. 5 minus 3 is positive 2. So as soon as you see this subtracting sign, you have to slow down and go a little bit more cautiously. So now this is 3x minus 2, looks something like that. It says take away an x. Whoops. I will take away an x. I've got one to take away. But it's now saying take away 3 positives. I don't have 3 positives, so I may have to bring in some 0 pairs. Now if I take away my x and I take away my 3's and I delete those, this is what I'm left with. So I'm left with 2x minus 5, which is the correct answer. And if we're going to look at this from an algebra standpoint, things to be worried about. The first bracket is pretty easy to drop. There's nothing around there. This subtraction says subtract the x and subtract the 3. Okay, and then you'd say 3x minus 1x is 2x. Negative 2 minus 3 more is negative 5. Okay, we're almost done. Here's the second last one, I think. Oops, moved them all around. Come on. There we are. I think this is the last one. So let's try this. Let's try it. Yeah, we'll do algebra tiles. Here we are. We've got them. So there's the x squared plus 4x. There's the minus 3. Now this says take away 2 positive x's. Well, we don't have those. We only have 1 positive x. So I could bring in a 0 pair. So there's my 0 pair. I have to take away 3 x's. I have enough of those, and I have to take away 5 negatives. I don't have enough of those, so I might bring in some 0 pairs. And now I should be able to take everything away that I'm supposed to. So take away 2, right here, take away 2 x squared terms. Well, I can do that, assuming I can get them all highlighted here. So they're gone. This says take away 3 positives, x's. 1, 2, 3. Get those and delete. And lastly, take away 5 negatives. So there we are. We hit delete. And this is what we're left with. So we have a final answer here of 1 negative x squared plus 1x plus 2. And if we're going to write this out algebraically, there's nothing on the first bracket to worry about for subtracting, so I can just drop that bracket. This subtraction sign here gets applied to all of my terms, so I'm going to subtract the 2x squared, I'm going to subtract a 3x, and I'm going to subtract the negative 5, and I'm going to put a big warning on that one. We have spent some time talking about subtracting negatives. Okay, so I'm just going to move all of this down so we can see it a little easier. There's the x squared, there's the 4x, there's the minus 3, minus 2x squared, minus 3x, and here's the one I'm going to put it in red because it's the dangerous one. If you subtract a negative 5, that's the same as adding 5. And now if we collect like terms, x squared and negative 2x squared gives me negative 1x squared. 4x's minus 3x's gives me 1x. And lastly, negative 3 plus 5 gives me the plus 2. Okay, so there's nothing there that's really over the top, but you really have to pay attention to details. Here's some questions to try from your text. Thanks for tuning in.